Spin relaxation is a key process in nuclear magnetic resonance (NMR) spectroscopy that describes how nuclear spins return to their equilibrium state after being disturbed by a radiofrequency pulse. When spins are initially aligned with the external magnetic field, they are temporarily displaced by an RF pulse, causing them to lose their original alignment. This process is governed by two primary mechanisms: spin-lattice relaxation, T1. This describes the exchange of energy between the nuclear spins and their surrounding environment, the lattice, leading to the recovery of magnetization along the longitudinal axis, z-axis. Spin-spin relaxation, T sub 2. This involves the interactions between neighboring nuclear spins, leading to a loss of coherence in the transverse plane, XY plane, and the broadening of signal peaks. Understanding these relaxation processes is crucial because they affect the quality of the NMR signal, influencing factors such as signal intensity, line width, and relaxation delays. By controlling and understanding these processes, researchers can optimize NMR experiments, improving the precision and clarity of data and enabling deeper insights into molecular structures and dynamics. Spin lattice relaxation, T1, is a fundamental process in nuclear magnetic resonance, NMR. It describes the energy exchange between nuclear spins and the surrounding molecular environment, often referred to as the lattice. Spins undergo transitions between higher and lower energy states, releasing or absorbing energy in the process. This transition helps to align the spins with the external magnetic field. The mechanism involves energy absorption or release, which enables the spins to return to a state of equilibrium with the lattice. This energy exchange is essential for the recovery of magnetization along the z-axis, the direction of the external magnetic field, B0. The impact of T1 relaxation is most noticeable in the recovery of magnetization, which is critical for NMR signals. The time constant T1 characterizes how quickly spins return to equilibrium, which influences the overall signal intensity and relaxation delays during pulse sequences. The rate at which T1 occurs plays a key role in determining the quality and precision of data obtained in NMR experiments. Now, let's dive deeper into the factors that influence T1 relaxation. Molecular motion. The speed at which molecules move plays a critical role in the efficiency of energy exchange between nuclear spins and the surrounding lattice. When molecular motion is faster, the interaction between the spins and the lattice becomes more efficient, resulting in quicker transitions between energy states. This leads to a shorter T1 relaxation time, meaning the spins return to equilibrium faster. Essentially, more dynamic molecular motion promotes rapid energy transfer, facilitating faster recovery of magnetization along the z-axis. Magnetic field strength. The strength of the external magnetic field, B0, also significantly affects T1 relaxation times. When a higher magnetic field is applied, the spins align more strongly with the field, leading to a stronger polarization effect. In such a scenario, the relaxation process is typically slower, which means the T1 time increases. This is because the energy exchange between the spins and the lattice becomes more complex in a stronger magnetic field, requiring more time for the spins to return to their equilibrium state. Intermolecular interactions. The nature of the interactions between neighboring molecules also influences T1 relaxation. When molecules have stronger intermolecular interactions, such as hydrogen bonding or van der Waals forces, they facilitate faster energy transfer between spins and the lattice. These interactions help to speed up the relaxation process, resulting in shorter T1 times. In simpler terms, molecules that are more tightly coupled will lead to quicker relaxation compared to those with weaker interactions. Temperature. Temperature has a direct impact on the dynamics of the molecules. As the temperature rises, molecules move more vigorously, which increases the rate of energy exchange between the spins and the surrounding lattice. At higher temperatures, the rate of spin lattice relaxation accelerates, leading to shorter T1 relaxation times. However, this relationship is not always linear and can be influenced by the nature of the material and the specific molecular dynamics at play. In many cases, increasing the temperature can lead to faster recovery of magnetization along the z-axis. Spin-spin relaxation, T sub 2, is a process where energy is exchanged between neighboring nuclear spins. This happens without any energy being lost to the surrounding environment. The local magnetic fields around the spins cause them to lose their phase coherence, meaning the spins no longer stay in sync with each other. The impact of T sub 2 relaxation is important when looking at NMR or MRI signals. T2 affects the shape of the signals we see. If T2 is short, the signals become wider and less sharp. If T2 is long, the signals are sharper and more defined. In simple terms, T2 relaxation helps determine how clearly we can see signals in NMR or MRI scans. Short T2 leads to blurry signals, while long T2 results in clear, sharp peaks. Understanding this process helps improve how we interpret and use these technologies for imaging and analysis. Now we're comparing T1, spin lattice, and T2, spin-spin relaxation, based on several key features. Energy exchange. T1 involves energy exchange between the nuclear spins and the surrounding lattice, the molecular environment. T sub 2 involves energy exchange between neighboring nuclear spins themselves, without interaction with the lattice. Direction T1 affects magnetization along the longitudinal axis, z-axis, meaning it impacts how spins realign with the external magnetic field. T sub 2 affects magnetization in the transverse plane XY plane, meaning it impacts how spins lose their coherence in the plane perpendicular to the magnetic field. Effects. T1 influences signal intensity and the recovery time of magnetization along the longitudinal axis. T sub 2 primarily causes line broadening and defacing of spins, which impacts the sharpness of NMR peaks. Typical time scale. T1 generally has a longer time scale compared to T2. T1 relaxation times are usually longer because it involves a more complex energy exchange between spins and the lattice. T sub 2 relaxation times are shorter, as they reflect the interaction between spins themselves, which is a faster process. Understanding spin relaxation is essential for interpreting NMR spectra and designing effective NMR experiments. Relaxation processes, such as T1 and T2, have a significant impact on the signals observed in NMR. These processes influence signal intensity, line width, and relaxation delays, all of which are key factors when analyzing NMR spectra. By understanding how relaxation works and what factors affect it, researchers can make more informed decisions when setting up their experiments. For example, they can adjust experimental conditions to optimize the quality of the data they collect. This can include improving signal resolution, enhancing contrast, or reducing noise. Relaxation processes also provide valuable information about the structure, dynamics, and interactions of molecules. For instance, different relaxation times can reveal insights into how molecules move, how they interact with each other, and even how they respond to external influences like temperature or magnetic field strength. Both spin lattice, T1, and spin-spin, T2, relaxation are key processes in NMR that have a direct impact on the signals we observe. These processes influence signal intensity, line width, and the relaxation delays that occur in the NMR spectra. Understanding how these processes work helps in interpreting the signals and improving data quality. Several factors affect relaxation rates, including molecular motion. Faster motion leads to quicker relaxation. Magnetic field strength. Stronger fields can lengthen T1 relaxation times. Intermolecular interactions. Stronger interactions lead to faster T1 and T2 relaxation. Temperature. Higher temperatures typically lead to faster relaxation. These factors must be carefully considered when designing NMR experiments to optimize results. Understanding relaxation processes is essential for interpreting NMR spectra accurately. By knowing how T1 and T2 work, researchers can design effective NMR experiments that yield high-quality data, which is crucial for exploring the structure, dynamics, and interactions of molecules.